So this New Year's Eve, many people around the world will be tuned in to the famous ball drop of Times Square, New York City. But what is this ball? Well, it's a timer ball, and it's an ancient maritime chronological device that ships, when in port, would pay attention to a ball atop a large, tall structure, and when it dropped, they would set the ship's chronograph, and they knew exactly what time it was, and time was used for them figuring out where they were on sea when they were away from port. Well, just as there's a fascinating history behind timer balls, there's an interesting physics as well. We can study with SOLIDWORKS simulation tools a lot of different physics. Here is a motion analysis where we drop the ball. Right inside SOLIDWORKS, we're able to extract forces, accelerations, and velocities of our structures. Let's go ahead and look at some of those results right now. With respect to time, we can take a look at the linear accelerations that the ball structure, a welded steel structure with a fabric coating around it, what types of accelerations it experiences. So we'll go ahead and select the component of acceleration that we're interested in relative to the face of the timer ball, and we'll plot that against time. The linear acceleration is fairly consistent until it has an impact, and the restitutive forces are captured, and we know that at time 0.75 seconds, that is our peak acceleration. But what do we do with information like this? Well, if we're tasked with designing a new timer ball, or maybe we need to change an old design and change it because it's been having some problems in the field, we can export or import the motion loads, export the loads into structural analysis by choosing that correct time frame, acting on the particular components in question, and we can perform structural analysis right within SOLIDWORKS using the same tools. So I'll change to that 0.75 seconds, and we can see how we can use those loads in a structural analysis. Let's open up now the timer ball's welded steel structure in its own window, and we can perform a variety of different analyses tasks, starting with those loads that we got out from the motion analysis tool. You see it's a very simple structure. There's some plates and bands that are bent and formed and welded together. Opening the part in its own window, we can see that we have a variety of configurations and some studies that I've already ran. Let's take a look at what we've done so far, and we'll perform some new analyses as well. My parts come over, my materials are already assigned, and I'm ready to perform analyses to extract things like deformations or stress. My motion loads are brought over as boundary conditions, and I can quickly and effectively run this design right here inside SOLIDWORKS. But this is just an artist's template, a place for me to start. For if I copy this study, you can see I can perform advanced analyses, such as dynamic analysis. Now, dynamic analysis, in this case, refers to the forces and effects of gravity or other loads acting with respect to time or frequency. So whereas we had performed a rigid body dynamics analysis with motion and used one time step to perform a static analysis, now I can create an acceleration-based dynamic analysis on the structure itself. We'll change to using G's, and then we'll plot out an excitation curve. This would be the amount of G's with respect to time, and we'll do just a very simple triangular wave. At time 0, there is no load. At time 0.5, 100% of the load is applied, and then we ramp it back down to 0. Let's take a look at that a little bit larger. If you have more complex loading histories, we can save those as curves and import them. Let's add a 10G load in one of the directions. We can do side impact load, a vertical drop load, or we can mix and match and combine load cases in a more intuitive way. Let's keep things simple, and we'll just do a 10G impulse load using that triangular wave. Being that this is a fully dynamic solver, we can also add the damping effects, either through the shape or through the material. Given that this is a welded steel structure, I'm going to use 5% damping, which is a pretty common value. And then, because I could be generating quite a bit of data, I want to be cognizant of that and only save out those steps that I believe are going to be the most necessary, and making sure that I'm producing enough steps to increase my granularity so that I have some good accuracy in my results. And I can make better and faster informed design decisions. Maybe through this analysis alone, we understand why the product is having some problems, and we're ready then to analyze some potential other solutions. Or maybe, under this loading case, there is no problems and there's something else going on with the use case. Either way, this is an exploratory tool. It's easy to set up, it runs quickly, and it gives us the information we need to move forward with making decisions on our design. We'll save out fewer time steps up front, fewer results plots, than we will later when we expect the dynamic effects to have a greater influence on the design. Save our work, and we'll solve it. Once it's solved, post-processing is fun. Here's the 10G response of the structure. But much like we did in our motion analysis, I'm interested in the response with respect to time. And using my probe tool, I can choose a piece of the geometry and see how that part of the geometry has responded with respect to the stresses in time. At any point that the material is exceeding its yield value, we know that we have a nonlinear problem, and we have the tools to solve that too. But going back to other aspects of the design, a dynamic analysis is just another part of a broader suite of tools, and the drop test is yet another one of those tools. Here we'll animate the ball as having been dropped from 3 feet onto an infinitely rigid plane. We can see the shock wave propagating through the structure. Like in our dynamic analysis, we can probe upon the structure and get the response of the structure with respect to time. Here, the solution hasn't finished. We should rerun this, make the time longer, let it bounce around a little bit more. And we can explore this design because it's a parametric model inside SOLIDWORKS. I'll use this static analysis to illustrate this. Using what's called design studies, I can capture various parameters of the model or parameters of my FEA studies and link those parameters to values that I want to vary. If, for instance, our customers think that the design is not robust enough and that a globe made out of 4 bands is inadequate, we can quickly test a couple other design iterations and see how they respond with respect to one another. So here I'll create a parameter for the number of instances in a pattern. Notice I can choose thicknesses, radiuses, lengths. I can also grab material properties, the size of my elements for a mesh, the value of a load. For example, that 10G load and from the dynamic analysis, we could add as a parameter into our design study and can vary its value. But once I add parameters, how do I track the output? If we're going to test 3 variations, 4, 5, and 6 instances, what do I want to look at? Well, those are called sensors. We can constrain the output by tracking sensors. Sensors can be used anywhere in simulation or just in SOLIDWORKS in general. Here I'll track the amount of deformation in a particular design aspect called the resultant displacement. That'll capture displacements in X, Y, and Z. And I'll look at the worst displacements when I run these 3 analyses. And I can see if there's any change, if adding more bands makes this a more stout or more robust design. Some people might call this sensitivity analysis. And once the software is done processing our different combinations, we can interrogate it, looking at those constraints and seeing if we've improved the design, made it worse, or in this case, it had no effect under this particular loading case. As a good engineer, I want the whole picture. And from a fabrication standpoint, it may be more costly, more challenging to make this with more bands. We may have already had the most optimal solution. But with tools like SOLIDWORKS Simulation, I can explore that, verify it, and validate it. All of these results can be saved out as reports. Plots can be saved as images or animations. We can use other tools such as Microsoft PowerPoint or Word. Or we can save this content as SOLIDWORKS eDrawings, which is lightweight, gives people the opportunity to mark up, and yet fully explore the 3D results. So this New Year's Eve, as the ball's dropping, and you're thinking about what promises to make for the year ahead, think about using SOLIDWORKS Simulation.